So what we're going to try and do here is put some of the sediment-hosted copper silver mineralization drilling and the targets in context. We've drilled 6 holes now, and we're beginning to understand the system quite a lot better. This is a list of requirements by Murray Hitzman and his group as to what a red bed basin should have in it in order to have real potential for sediment-hosted copper and potentially copper-silver. And what I'm going to try and do is we've had a lot of feedback that okay, you guys are always excited, you're always positive about what you're seeing, but why can't you hit anything in the drilling? And I just wanted to get this across because our red bed basin is called the Chapisa, so it's about 140 million years through to about 170 million. So our Chapisa, Murray Hitzman wanted to see at least half a kilometer of thickness of red beds. We've got at least 3 times that. He talks about mafic or intermediate volcanics, and the mafic volcanics are just volcanics that are lavas and intrusives that come up into the crust that just have a particular composition. They come out very hot. And we know that we've got this right in the middle of the Chapisa. We've got a formation where there are 4 different kinds of lava, and we'll talk about that a little bit later. But more importantly, our Chapisa it's not the normal red bed. It only has a quartz. So most red bed basins are arcoses, which means that they've got maybe 50% silica grains in them, the rest is feldspar. Ours only has less than 10% silica. So instead of it being a sand, it's actually just a mass of tiny little sand-sized volcanic fragments. So, and all of those fragments are this mafic lava, which is a fantastic source for copper, lead, zinc, silver, and then a couple of others that I won't even talk about because we don't want to get people's expectations up. And also the basin must have something that's going to pull the copper out of solution, and that can be a number of things. Most of our high-grade samples that come from surface have always got some black in them. Those are carbonized little wood fragments or leaves or whatever, and then oil and gas. And we know that the sequence underlying our red beds is a source of oil and gas that's produced from Ecuador. Evaporites, we now know that we've got, we suspected that we had evaporites, and we've now drilled evaporite in hole 6 at Tsenken in 1. And we can also see where that salt actually came from in the sedimentary layering that's under the red bed basin or the Chapisa basin. He also wanted to see evidence of widespread leaching of minerals. So the red beds, we know that our red beds are a better source of those interesting metals, the copper, lead, zinc, silver. They're a better source than most red bed basins, but he also wants to see proof that those little grains that make up the sand in the Chapisa in our case, he wants to see a footprint that those little grains have been attacked and rusted effectively, which makes them makes the whole sequence red. And he also wants to see evidence that there were reasonably hot fluids going through these basins. So we look for the little alteration minerals, which are mainly clay in this basin. They're a little bit different. And then, any deposit, you want a a source of metals as big as you can possibly get it. This is a big basin, but you need to squeeze all of that big volume. Imagine it as a sort of funnel. You want to take a big volume of fluid and squeeze it into the smallest place possible to get the grade that is likely to be form a deposit and be economic. And then you need a triggering mechanism to actually squeeze that fluid out of the rock. It's no use having it in the rock. It can sit there forever. You need a way of squeezing the basin. And there's lots of evidence of that in the Chapisa. With our drilling, we're seeing more and more evidence of it. But the very obvious evidence is that the Andes are right here. They are on the edge of the property, and the Andes obviously was immense force that's squeezing this basin, and it's basically like a sponge. The fluids that are leaching the metals are going to be stuck in the basin, and they can sit there forever. But we need to take that big volume and force it into a small volume. So we need that thing that's going to squeeze the fluids out and squeeze the sponge. So, just talking, I'm going to go from a slightly different point of view. We need a source of metals. For any deposit, you need a source of metals. You need some sort of transport mechanism, some sort of plumbing system to get those fluids out of wherever that metal source is into the place where the deposit is going to be. You need to be able to basically drive it along the plumbing system, and then you need the metal traps. And in sedimentary copper, silver, the salt is hugely important, and I'll come back to that in a minute. So we want not only the salt, but the gypsum and hydrite. The salt because it's got chlorine in it, and the gypsum and hydrite because we need the sulfur for that from that to develop the deposit. And then hydrocarbons also have sulfur in them, both in oil and in natural gas. So just looking at that first point, the source of metals. We've got this very thick sequence of red beds. Importantly, over 90% actually volcanic fragments, so fantastic source of metals. And we can see that the black mudstones, which are underlying the basin, they're also a good source of other metals, and they are the source of oil and gas. And then, copper-bearing porphyries like Warinsa, if they were to intrude red beds, all the low-grade material that's normally deposited at sort of 0.1, 0.2, 0.3% around the porphyry is just going to go into solution because of the salt. In our case, we've also got this Chapisa lava, or it's called the Miswaji, that is mineralized in places, and I'll come back to that in a second, mineralized with copper. So the basin as a source of metals, so this is just a very generalized vertical slice through the basin. So we've got our red beds up here, the Chapisa Formation. We've got this lava in the middle that we thought was a crucially important seal, and in a lot of our press releases we've shown that as a green line, and we've drilled for metal accumulations under the lava. We've also got the mudstone under here and the limestone that's in the older basin, source of hydrocarbons and other metals as well. So there's no problem with source. And this is a cross-section, and sorry, I haven't put the credit on here. This is from Solaris Resources, one of their 43-101s. And again, this is a vertical slice across Warinsa. And so this, the sort of purplish rock and this greeny yellow stuff is the porphyry system. So that is a source of metals, but what's important about this cross-section is that what's colored in green here is the Chapisa Formation. It's the red beds. So we know we've got a prime example of a beautiful deposit, 1% copper over 1,000 meters or whatever the guys are drilling there, and we know that that is intruding into the Chapisa. So it's a source of metals, copper particularly, and also a source of heat. We want the basin stewing as much as we can. This lava is about 150 meters thick, and so it's like putting a lid on a pressure cooker, and all this stuff under here is going to be stewing. If you were to intrude Warintza into this, it would not only put in metals, but it would put in heat to help leach those metals out of the red beds. So, how this is our particular example again. Our seal of the top, which is the volcanics, and we're looking at sort of folded sequences. And we've got the porphyry, like Warintza, theoretically coming into this. So we've got a source of metals in the red beds. And key to this is the salt, because salt is NaCl, and the chlorine from that salt keeps the zinc, copper, and lead in solution. And that can sit there while the metal is in, and silver, while the metal is sitting in that chlorine complex, they call it, while the metal is bound to the chlorine. That can sit there for hundreds of millions of years, because nothing's going to happen to it. It's absolutely stable. We need to get that fluid into a place where it's going to react and drop its metal out. So that's why we've been talking so much about the salt. And then obviously down here, the so-called Santiago Formation, limestone and black shales, source of petroleum. So we can put a big check mark against number one. Moving on to number two, how are we going to move those metals around? And what is the footprint that we can see that convinces us that those fluids have moved around the basin? So in terms of the salt, again, here's the metal and the chlorine complex. You have to have salt, and we've drilled it. The other thing that's just so very nice about this is that we can also see this so-called chicken wire texture. These are limestones from the Tiriashimpia area, from the drilling that we're doing there. And these textures are absolutely typical of an area that had salt in it, and the salt has flown out of there. So salt becomes very, very fluidized, and under certain conditions, and maybe with a little bit of seismic activity, the salt will move out of where it was originally deposited, and it moves along until there's a break in the sedimentary layering, like a fault, and then it'll go up the fault and sort of mushroom out. So we've got the salt, we've drilled it in hole 6 at Tsenken N1, and we've also got the footprint of where that salt came from down in this area where we're drilling Tiriashimpia. The evidence of the basin-wide fluid flow. This is actually the volcanic rock. This is a little quartz vein, about 1 centimeter wide, 2 centimeters wide. And it's got native copper and cuprite, which is a copper oxide mineral, in it. And this rock looks as though it's never seen a fluid. It looks like a horrible rock from an exploration geologist's point of view, because it's got these white feldspar crystals in it, beautiful crystals, and that under normal circumstances means that it's a disaster. This hasn't seen any fluid, but we know that it has. And what's happening here is that the feldspar is actually stable with the mineralizing fluid. The other bizarre mineral that we've got in here, well, it's not bizarre, but it's bizarre that it's preserved, is the augite, and it's you would expect it normally to have disappeared in the reaction from those fluids around the copper. But the fact that it hasn't, that it's stable, means that we're dealing with a copper-bearing fluid, or one of the interpretations is that we're dealing with a copper-bearing fluid that's got calcium in it. This is a calcium-bearing mineral. So we've got our first evidence that this basin saw quite a special fluid that was hot and it was full of calcium, and I'll talk about where the calcium comes from in a minute. This is, sorry, and I should have explained, these, the last graphic and this one, and I think the next one, is going to be of thin sections that are cut, the rocks cut into these very, very thin little wafers, and then light is passed through from beneath, and these are photomicrographs. They're photographs taken through a microscope. So this is about 0.2 millimeters, that scale bar. So we're going right down into the rock and looking for this footprint that the metals have been through there. So this is just don't. It's again an augite crystal. It was an augite crystal. This is the remnant of the augite in there, but it's been completely replaced. Large parts of it have been replaced by the copper mineral, and the original mineral that's showing up as blue here is just the grey here. This pale stuff in the reflected, the light that's coming through is the copper mineral. So again, we're seeing that a copper-bearing fluid was now starting. It was once stable with these minerals, and now it's starting to interact with them a little bit and precipitate copper. And then, just the last one on this, again, this is 200 microns, so 0.2 millimeters. This is an ilmenite crystal. Ilmenite is very, very stable. It's an iron titanium mineral. The black that one quite often sees on beaches is this mineral, very, very stable. But in our case, the ilmenite is starting to be replaced by hematite. So we see ilmenite in the core here, but hematite around the edge. So again, this is the footprint of an iron-bearing fluid. And sorry, just one more. Again, 0.2 millimeters in the pale, so it's exactly the same image. The pale is the copper mineral coming through here in these tiny little veinlets, and it's cross-cutting something that's called plagioclase feldspar, which normally just gets obliterated by alteration by the fluids that bring minerals in, bring the metals in. But in this situation, the plagioclase is just sitting there. The plagioclase is stable with the copper-bearing fluid, and that copper-bearing fluid is just precipitating the copper within a mineral that you normally don't see in deposits. So again, this says that the copper-bearing fluid is stable with sodium and calcium, and potentially a little bit of potassium as well. And the footprint of the metals and the deposition of the metals in the Chapisa is the mineralization that we're seeing at surface. And this is not quite as glamorous. We see a little bit of the green mineral malachite coming through, but this is the black is a copper-bearing mineral as well in what's quite clearly a sedimentary rock. So the third point, what is going to so we can see that we've got the footprint of a fluid. The whole of the basin has seen this fluid that can leach the metals. It's the right sort of temperature. How are we going to take that big volume and squeeze it into something that's high enough grade to be a mineral deposit? The first thing is faults. So in this cross section, this is between Ecuador and Peru. It was part of our justification for applying for the land in Peru. So we've got the red beds forming against these faults in a rift basin. And right from the beginning, we could see copper mineralization, the green and black in here, with fragments in it that looks as though it came from a fault. And then the classic red bed mineralization that was, in our case, has always got the black carbon fragments in it in the sedimentary layering. So the faults are important in moving the mineralization around. And this is just a little 3D block diagram just to try and illustrate that. So the copper would be moving out of the red beds, and the fluids would be moving along the sedimentary layering until it hits something like a fault, and then it's going to move up that so the fault can be mineralized, and then any reactive bed that's in our case got carbon fragments on it that's sitting within this sedimentary layering. So this is the sedimentary layering here, and this is looking at the one surface of the sedimentary layer. The whole thing would be carbon bearing, but then the copper would be coming up the fault and spreading back into the the reactive sedimentary bed, and that's where the deposit would be. And the perfect illustration of this is Kakula in the Congo, Ivanhoe's. This is close on 40 billion pounds of copper at about 3%. Here's the kind of fold that we were talking about. So these are red beds down here. This is an impermeable layer over the top of it, and the mineralization. These are little histograms, the red histograms, just showing the grade distribution. So the copper grade sitting right along that contact. So this is a vertical slice through Kakula. Notice the number of holes that they've drilled here. And this is a vertical view, just showing that this is very much a worm-shaped deposit. So the sedimentary layer would form, it would be throughout this area, but the copper is only precipitating in one place. And that presumably is because there's a fault up here or up here, and the mineralization is moving into that fold, the top of that fold. The other absolutely key thing that has come through just very recently, a discovery again made by Ivanhoe, this is again a vertical slice. The blue, so this, and the colors are grade, copper grade distribution. So we're seeing the classic sediment hosted copper here in this layer here, and then it's faulted down by this bonanza fault, and so that just moves like that. So you see the copper in this layer, and that's a more permeable layer, so it makes this is classic sediment hosted copper mineralization. However, this discovery is absolutely massive. On the fault itself, so the fault comes up here and it goes through there more or less, there's this huge mineralization that's about 30 meters wide and just extreme grade, almost 11% grade. And this has been absolutely crucial for our understanding of the Chapisa and what we're looking for in the Chapisa, because this is an impermeable sedimentary rock. So, and this unit here where the mineralization has moved along, that is a slightly more permeable unit. So we've got impermeable, permeable, impermeable again. And the fluid can't get into this impermeable rock, even if it was reactive, even if it was carbon bearing or oil bearing or hydrocarbon gas bearing, the fluid can't get into it. So in this particular case, Ivanhoe has made this incredible discovery right on the fault, because the fault is the only way that there's going to be permeability in this sequence. The pump driving these fluids. Again, we've got the list of things that happen in a normal red bed basin, like the Cutucu or the Central African copper belt that goes between Zambia and the Congo. And we've got ours, the Chapisa Formation, which we know is a little bit different because it's got all these volcanics in it. Faults in terms of a plumbing system, so important because of that last slide. We've got lots of evidence of them. Heat, we know that we've got things like Warinsa coming into the system somewhere, we don't know exactly where. And we've also got, there's some evidence of IOCGs, as there is in the Zambian copper belt. And we've also got extrusion, so lavas, those green lavas that we've had in all the profiles coming out on surface, and those things are coming in at about over 1,000 degrees or whatever. And then the basin, in terms of squeezing that fluid out, we know that we've got at least the Andes and a couple of other squeezing mechanisms. So the Chapisa basin has been moving around, it's been sort of pumped like an accordion. The red beds are normally permeable. The Chapisa is not. It's an absolute mess. And that is a curveball for us. So again, these are photomicrographs, the little wafer-thin slivers of rock where the light is being passed through from underneath. This is just taken from an oil reservoir rock, because oil reservoirs, we're talking about exactly the same thing. We're talking about the oil-bearing fluid coming from one rock and needing to get into another rock to make a reservoir. This is one of those wafer-thin slices of the Chapisa. Any sandstone within the Chapisa, it's an absolute myth. And it's not a sandstone, I'm using the wrong term. It's what they call, it's a volcanic sedimentary rock. It's a sedimentary rock, but completely full of volcanic fragments. So, and in here, I mean, you can see the odd little bit of quartz that's been labeled in here, but otherwise it's an absolute mess. You can't get fluid into a rock like that. So the red bed, in most of the drilling that we've done, cannot contain a copper deposit, or not a big one anyway. In terms of just going back to the faulting, because we need the faults to be able to drive the fluids and also to form pathways for those copper-bearing fluids. This is a map, so we're looking down from above. And as exploration geologists, we always get pretty excited when we see curves in faults. And I'll talk about why in a second. But this one, these two faults that were taken from satellite imagery and they've been confirmed by the field mapping, go and north is up that way. And let me just orientate you. These little red marks here are where we've drilled in Tsenken N1. This is a Tsenken N2 and N3 up in this area. And the red are the different drill holes that we have. That lava unit, the green layer on all of our profiles, it consists in a little bit of detail of 4 units, and the lower unit we've just mapped out here, so that unit would cover this whole area, and it extends up into Tsenken N2 and N3. But what is important about it is that it's a marker horizon. It tells us what is happening in the basin at that time. And these different shades of green, and this is just a blow up of this. The different shades of green, the darker the green, the thicker the lava. So what's happening here is the lava is relatively thin here, and this is a lava that, because of its composition, the minerals that are in it, is coming straight up from extreme depth. It's a primitive lava, and it goes from about 10 meters thickness down to about 60 meters thickness here. And it looks as though that change in thickness of the lava is coming where the fault starts to curve. So in other words, this fault had a hole next to it that was being filled in by the lava. And as we make that hole, so the deeper we make that hole, the thicker the lava is in it. And there are a couple of other illustrations of that. I won't go into that for time. So I just wanted to illustrate why that's important to us. One, it says that fault was moving at the time that the lava was developing, and we need to see faults that were moving during the basin development. So the lava layer is part of the basin, and just the fact that it's a lava helps us to distinguish it so we can see what's happening with it. So what I've just done is I've just traced over one of these faults here that we think is related with this change in thickness of the lava. And all I'm going to do, no, I can't do it here actually. Sorry. Okay, we're just going to have to imagine it. So if one were to move, a way of making a hole here is to move this fault in this sense. Because as you move it, if you can imagine this line moving up relative to the fault line, as you move this block up, so you're going to create a hole here. And as you create the hole, the sedimentary basin tilts down into it, and that's why we're filling that gap with lava. So we know that this fault was moving at the time, and if that one's moving at the time that the red beds were deposited and the volcanics, if that one was moving, that one is probably moving, and this one probably as well. But in looking at this fault, we would not be so interested in this part of it. We would be interested in where it starts to curve, because that's where the biggest hole is going to be. So going back to that slide of the copper mineralization from Ivanhoe's presentation, the copper sitting along that fault, that's exactly what happened there. That fault opened up and the copper mineralization went into, was deposited in that gap made by the fault. So we've got big check marks against these three. What about metal traps? We've seen that we've got evaporite, and that is important in getting the metal into solution out of the red bed because it's got the chlorine in it. Okay. After the chlorine, we can sort of forget about the salt for a little bit, and then we focus on the other two minerals that form with the salt in evaporite sequences. And evaporite sequences are just where there's been a very shallow sea or whatever that's been isolated, and then in hot areas around the Gulf today, for example, you get the evaporation of the water and you leave the salt behind. So the gypsum is important because it's a source of sulfur. So we know that we've got the metals in solution, or we're very likely to have the metals in solution. Now we need to find the thing that's going to precipitate and precipitate the copper. And all of these sediment-hosted deposits, the mineralization is made up of copper sulfides. So we need a source of sulfur. There's a source of sulfur out of gypsum and also anhydrite. They're so-called sulfide minerals.
Black shales full of sulfur.
Yeah.
Yeah. Iron.
And and then hydrocarbons. Very often, when we break those black shales, you can smell the sort of diesel smell, and then we know from the oil industry that they're a source of hydrocarbon, which is a good reductant for the copper bearing fluid as well, and a good source of sulfur. And just bringing up this slide again, so just to reiterate that this is impermeable, this is impermeable. So this would be very, very much like the Chapisa, where Ivanhoe come up with this discovery. we're going to see no permeable units in the Chapisa, and we can see that. We can see that where the permeability increases, where the sediment is a little bit cleaner, a little bit more quartz in it, we see the fluids getting into that and bleaching the rock, and they leave behind a tracer which is sometimes illite and sometimes it's prehnite. They're just two alteration minerals that tell us, hey, these were hot fluids. But we haven't hit a horizon in our drilling in the Chapisa yet that has really nice permeability with some trap, some chemical way of getting the copper out of solution. So from what we've seen in the Chapisa so far, this is our principal target. And if we just go back to this slide, sorry. We already know from the lava, and without the lava in the sequence, we would not have been able to identify this because one red bed looks like another. We think that this part of this fault would have opened up and be a great target for sort of Ivanhoe, this kind of mineralization. So, sorry, there's a mistake on this. That should be the Chapisa is impermeable. Let me say that again. I said in most basins, most red beds are permeable. And that's why we originally went for the drilling under the lava. We've now realized that we've got a curveball. The Chapisa is not permeable. So we have to change our thinking. If you're in a permeable basin, you need to find the trap sites that are impermeable. And in the Chapisa, it's the other way around. We're now, instead of looking for trap sites, we're looking for permeable layers. And we need a reductant in those permeable layers, either bitumen or pyrobitumen or plant fragments or whatever. And the other source of sulfur is the evaporites, and that are related with the salt. So our drilling up till now in the Chapisa has been mainly focused on, and this is more or less the same sort of graphic that we've had in some of our press releases, the lava seal. We know that this is a source of hydrocarbons. The gas and the oil would have gone up into these trap sites. The oil guys are always drilling these. We're talking oil geology here. But in our case, we know that we've got salt, we know where it's coming from, we've got the source of oil, we've got the porphyries coming in here, and the Chapisa is a great source of metals. So our thinking on our drilling to find the copper under the seal was absolutely correct in a permeable basin. But the problem is that the Chapisa isn't permeable, and we didn't know that until we drilled. Or this part of the Chapisa basin that we've focused our exploration on. So this is just the illustration. It's been in a couple of the press releases, an east-west profile, quite a big profile, about a kilometer here and about a kilometer, so no vertical exaggeration. Big fault system. We now know from the lava which way that fault was moving and when it was moving, which is fundamentally important. And originally on this graphic we had drawn the evaporite being controlled by the faults that are coming out of this material here, so that we know that the salt was here, where this yellow layer is, come out along the faults. This fault probably has salt on it as well, it would make sense. And we drew the salt originally down here somewhere. We've now hit it in hole 6, so we know that we were sort of underestimating the extent of the salt. And this is in cross section, in a cut through the Tsenken area, and in 3 dimensions. This would probably be a salt wall. That's what we see in the seismic data from the same basin in Peru. So a good idea, but the permeability is a bit of a curveball. So just going back to putting Tyria Schimpia in context with this, Tyria Schimpia, metals, lead and zinc and silver in sulfide. It's crucial that it's in sulfide as an indicator for us. So we know that we're getting the sulfur from somewhere, and in fact this is a bit of sulfate from Tyria Schimpia, so we know that there's an excess of sulfur. So sulfur source in this area is not a problem. So we've got a metal source in the Red Bed Basin, we've got a sulfur source, at least at Tyria Schimpia, and we just need to get those two things together, and we need to be thinking about where that's going to happen. So on a big scale, this is Gregor Horg's graphic of the metal zoning in the Fuship, and you also see it in parts of the Zambian copper belt. Hematite, we've drilled that out at Tsenken, at N2 and N3, and in fact we're drilling lots of magnetite as well. That's secondary magnetite. In other words, it's magnetite, it's another iron mineral that's been forced into the basin. So we've got this red part, we've got this part up here, and we just have to nail where the copper-bearing zone is. And our thinking on that at the moment, we've put this graphic out in a press release as well, is this is our lava seal across the top here. We drilled underneath that, thinking that that would be the place that the copper would be concentrated. Because of the lack of permeability, it didn't work. We were wrong. We've drilled the hematite and magnetite in N2 and N3. It looks as though that's part of the same system. And we're drilling the Tyria Schimpia zinc silver now, and we're seeing really beautiful permeability in the very top of this unit. So theoretically, if we go down at Tsenken, we're eventually going into the same layer that's mineralized, that's got this mineralized Tyria Schimpia, that's got this beautiful permeability in it, and it holds hydrocarbon. You can see pyrobitumen in it. We just need to find where this is, and this is the thing that we're drilling at the moment. Just focusing in on Tyria Schimpia a sec. So that would, so in this vertical profile, I should have said that, just a very simplistic and idealized one. The whole thing is tilted a little bit, so today's erosion level is something like that. So at Tsenken, we're looking up in this area, whereas at Tyria Schimpia, this is actually its surface. Sorry, still haven't got to it. This layer down here, just homing in on where we've seen that at Tyria Schimpia. This is a vertical profile of a carbonate ramp, the kind of, flying over the Caribbean or something. You see the islands with those big white sheets around them underwater. That is mostly carbonate. And so what we've got here in these two black lines is just different tidal levels of the ocean. So down at depth, and normally these things are ramps, so they're very shallow water, and then they go deep pretty quickly. And these are, this is taken from a study of 3 of those little, very detailed laminae of 3 different places in hole Tsenken, Tyria Schimpia, hole 1. And this study that was done by a bunch of guys in Quito, absolutely top class. They identified that part of hole 1 at Tyria Schimpia has hit this part of the system, but crucially, it's starting to be very shallow water, and that ties with some of the features that we've seen in the field. And even more importantly, here, they've identified this kind of rock, which is right next door to the Sapka environment. And the Sapka environment is where, in very shallow seawater, you get huge evaporation in hot climates of the water, and you're left with salt and the sulfates behind. So this is an evaporite sequence. So it makes sense with those chicken wire textures that we're seeing in the core. These carbonate specialists identifying that we can see the rock that you would expect to lie right next to that. And behind a Sabco environment, sorry, I've changed up their diagram a little bit, are red beds. That's exactly what you would expect to see. Red beds are formed in a continental setting. And then, so I've changed this up a little bit to put the Chapisa in there, and then the volcanics that we've seen, and a Warinsa kind of porphyry. So the whole thing comes together from an absolutely microscopic level that we're seeing in these laminae right through to what the guys are publishing out of Warinsa. Gregor Borg was here a couple of weeks ago, about a month ago, and to me the most critical thing that Gregor switched on to was the fact that in our thinking, and I've been saying it, and it's been shown like that on all of our vertical cross sections. I'm showing there the limestones and black shales, the Santiago Formation at the bottom, and the red beds, the Chapisa over the top. That is a slice through the basin. But in terms of time, in the real world, and you see this in the Caribbean or anywhere else, you see this shelf environment forming at the same time that all of this is forming and the volcanism. So if we were to take a timeline at 155 million years, or whatever number you want to choose, we would have this whole sequence forming, and we would call this the Santiago Formation, which we think is being lower, and we would call this the Chapisa, and we would call these the volcanics, and the porphyries would be called something else. And we tend to think about them as having some different time, so all forming together. And the way that you get the red beds over this is just to have the river system encroaching on the ocean system, so you end up over time with the red beds sitting on top of the limestones. But basically, we've got every part of the system, and this is why we're so excited about Tsenken. We are getting close to nailing it. So basically, in terms of where we go next in our drilling at Tsenken, we can see the chicken wire texture. We know where the salt and, more importantly, the sulfate species have come from. We've drilled the evaporite mushroom or dome, and what we need to do to find the permeability, because none of this is permeable, is to get down in the sequence a little bit down into this area where we know from our Shimpia drilling that there's a permeable end, and that's what we need to do next. So what we're looking for, we know that these faults will probably bring up copper, so we're going to be looking for copper along permeable units just into that limestone sequence under the fault, and also we probably have the same thing going on in this area. And so what we're drilling at the moment is this stuff, but instead of it being in this profile, we're drilling it further away, where this has come closer to surface, so we don't have to drill such deep holes. And this stuff just needs some agreements from the landowners that takes a couple of months and a drill camp to be built, and then we need to get in and drill that as well. So we have every single element, and it's just a matter of having put it together in the right way. Yes, sir.
Can you follow up on the 2D realizing for the system? How long is that?
These are the same faults, and that's a great question. These faults are the ones that go into Shimpia. So we know that they're precipitating zinc and lead and silver up in Shimpia, and here we think that they're going to be depositing copper.
So just thinking.
Oh, sorry, in length, that's about, the whole thing is about 50 kilometers.
And the fault system is 50 kilometers.
Yeah.
So we got structural issues. 50 kilometers. That increasing in volume is a possibility of disclosing that.
Yeah, and just going back, I glossed over it a little bit. Sorry, let me just go back to this. Looking on this scale, we're looking at about, sorry, there isn't a scale on here, about 10 kilometers or so. So the most obvious target is this curve. But then each one of these little jogs, every time it changes direction, that's going to be an interesting spot because it's going to be where it's open. Anything else? So this is why we believe we're getting close to it. So this is what our target is at the moment. So on this profile, interior Shimpia would be here, outcropping its surface, but we believe that it could link up with copper mineralization there, and we would obviously like this copper to be a lot more extensive as well. There's absolutely no reason that it can't be. So that's the sort of model that we've got in mind.
So we can go from the east side, it's pretty deep on the west side, it's pretty shallow.
Yeah, and we've got very little constraint on this over here. We know that this is a normal fault, so the sense of movement has been like that. So we know that this is reasonably shallow, but there's minimal constraint on what depth. That the interesting horizon could be 100 meters below surface. We don't know. We're going to have to drill a near vertical hole here to see what's going on. And now that we've got this concept, we can use the mobile MT a little bit more cleverly. But of course, the evaporite with the salt in it is going to conduct like mad.